Hi everyone, in this video I'm continuing to work through question 15 part B of the 2020 Extension 2 trial exam from Ascham. So it's a two-part question and I've already worked through part 1 in a prior video, so have a look at that if you haven't already. And here I'm going to focus on part 2, which says sketch y is equal to d dx of g of x, noting that g of x is the inverse of f of x. So yeah, let's take a look. So here we're being asked to sketch this derivative of the inverse, and it might be worth just expressly noting that really what we're being asked to draw is the derivative of the inverse function of x. And noting that in part 1, we've just worked out f of x, and we've worked out a sketch of kind of what that looks like in general. We don't know exactly kind of the values, but we know in general the shape. Well, I think we can tackle this derivative of the inverse in 2 steps. I think it makes sense to first sketch up what the inverse would look like, and then from that sketch work out what the derivative of that inverse would look like. So that's what we'll do. So I might just draw up an axis where we'll focus first on just what the inverse looks like. So let's get an axis going. So this should work. So I'll just label our x and y, so x for the horizontal, y for the vertical. And it might actually be helpful if I note maybe in black, I'm just going to note the curve y is equal to x, which I'll just use my grid paper to make sure I kind of get this right. So I want this kind of 45-degree tangent for y is equal to x. I think that looks pretty good. So let's just draw that. And the reason this is useful to draw is because hopefully you know from your Extension 1 studies, I think it's Extension 1 that you probably first learn about inverse functions in any kind of detail. We kind of learned that the inverse, you're effectively just swapping x and y. So wherever in the original function you had an x, you'd put a y, and wherever you had a y, you'd put an x, and then you do your rearranging to kind of find the inverse. But in terms of charting, one way you can think about it is you're reflecting the curve about this line y is equal to x. That's a kind of graphical way you can think about the inverse function. So if I kind of just overlay our original curve, our y is equal to fx. So remembering we kind of had at the origin, it kind of had this tangent of 1, and then it kind of came up and flattened out, and then it came down and flattened out. That was the basic shape of our y is equal to fx. So noting that that's y is equal to fx, the inverse we can sketch quite easily by just kind of reflecting about this line y is equal to x. So we know at the origin the curve is essentially the same because we have this tangent of 45, but then basically we want the distance to kind of, now instead of always being below this y is equal to x, we're always going to be above. So the curve kind of ends up like this, in x being greater than 0, and then like this for x being less than 0. And I probably haven't like drawn this perfectly, but I think the key point is that you're kind of always above this line y is equal to x now, and always below it. For x greater than 0, you're always above, and for x less than 0, you're always below, and you're reflecting about this line. So that's the curve y is equal to the inverse, so the inverse function of x. And from that, we can now think, well, what will the derivative look like? Because remember, that's what we're being asked to sketch, the derivative of the inverse. So I might just draw up another axis, so that this one doesn't get too messy. So let's come down and then across. And just like we did for part 1, I think the key here in terms of jumping from a function to its derivative in terms of curves, it's just kind of thinking in general, what can we know about, in this case, what can we know about the derivative based on the shape of the curve. And if I just, I'll just move my ruler, if we just jump back to part 1, remembering when we were starting at the derivative and coming back to the curve, we noticed that because the derivative was 1, we had this tangent being kind of this straight line at a gradient of 1 or an angle of 45. Well, now we're kind of working the opposite. We know we've still got this angle at 45 at the origin for our underlying curve, in this case the inverse, y is f of negative 1x. So we know that the gradient, the tangent at this point 0, must be equal to 1. So that's probably the first thing we can note. So if I just maybe note this as being the value 1, I know that our y is equal to the derivative of in the inverse function of x will hit this point 0, 1. And now we have to ask ourselves, well, what happens? Is the gradient greater than 1 or less than 1 for x being greater than 0 and for x being less than 0? If I focus first on x greater than 0, because the curve is always above this line y is equal to x, we know that its steepness must be greater than this gradient of 1, because if it was equal to 1, it would lie exactly on this curve, but because it lies above the curve, it must be greater. And notice that the further away we get from x, the steeper this curve is getting. So in terms of just thinking generically, and again, this won't be a perfect curve, but we know that as x gets bigger, the gradient gets bigger and bigger and bigger. And it's exactly 1 at x is equal to 0, and then it's close to 1, and then it gets further and further away from 1 as x gets further and further away from 0. So that kind of deals with positive values of x. Now if we think about negative values of x, well, notice that it's still a positive gradient, because as x gets bigger, the y values get bigger for this inverse function. And again, as we're close to 0, the gradient is very close to 1, but as we get further and further away from 0 in the other direction, the gradient gets steeper and steeper. So still a positive gradient because values get bigger as x gets bigger, but it's just going in the other direction. So I can draw this basically like that, and ideally if I drew this well it would be symmetrical, but hopefully you get the idea. We've kind of reverse engineered kind of what we were doing in part 1. We're just going the other direction in part 2, going from a curve to its derivative instead of going from a derivative to its curve, but it's the same set of ideas and same set of principles that we're making use of. I think what makes this a little bit trickier is we first need to think about the inverse function before we can then go to the derivative. But now that we've got our inverse function and we've noted the key, I guess, behavior, we've now got our curve. So this would be y is equal to the derivative with respect to x of the inverse function of x. Boom! So hopefully that made sense and you found that helpful. As you can see, there's not a lot of kind of working out or algebra required here. I think the essence of this question is very much like part 1, just testing your ability to jump between a curve and its derivative, or vice versa, without actually knowing the underlying function. And I think for this part 2, you also had to be quite comfortable with the idea of what is an inverse function, and this idea that you're reflecting about this curve y is equal to x. And so I think taking those kind of basic foundational ideas all together, you can, without too much trouble, I think, get to where you need to get to. So hopefully that's all made sense with this question and you've been able to follow along. And yeah, tick boom.